Mọi người nghe rõ đúng không ạ? Coi như nếu mà như vậy thì chắc là mình nghĩ thời gian nó cũng cũng hết 2 phút rồi đó, thì thôi chắc là hôm nay mình bắt đầu luôn nha. Thì trước hết cho phép mình giới thiệu một tí xíu. Mình là Phương, bên phía công ty bên ASIC. Thì như các anh chị cũng biết đó, ASIC và Keysight có tổ chức phối hợp một cái buổi webinar. Nó gồm 5 cái buổi khác nhau và nó có 5 cái topic chuyên về cái mảng high speed digital. Thì mình cũng xin đại diện bên phía Keysight và ASIC cảm ơn các anh chị rất là nhiều đã dành cái thời gian tham gia các cái buổi hội thảo số 1, số 2, hôm nay là buổi số 3. Và cũng hy vọng là các anh chị có thể cùng đồng hành với ASIC và Keysight trong 2 cái buổi tiếp theo nữa, là buổi số 4 và buổi số 5 để tổ chức vào tháng 10 và tháng 11. Thực ra là các cái buổi webinar cũng được bên phía bên Keysight và ASIC chuẩn bị rất là kỹ lưỡng về mặt nội dung. Các cái buổi topic nó sẽ được nói chuyện theo một cái nội dung là từ cơ bản tới nâng cao, để cho tất cả các anh chị cùng theo dõi và dễ nắm bắt được các cái nội dung mà diễn giả nói. Thì mình cũng xin nói lại luôn á, là chia sẻ lại một tí xíu để cho các anh chị, nếu hôm nay là cái buổi đầu tiên tham gia thì nắm thêm cái thông tin là buổi số 1 thì bên phía bên Keysight có những cái thông tin rất là basic về signal integrity, tức là cái tính toàn vẹn của tín hiệu trong high speed digital, thì mọi người sẽ quan tâm đến cái đó rất là nhiều. Rồi sau đó thì cái buổi số 2 mình sẽ nói sâu hơn một tí xíu về việc phân tích cái tính toàn vẹn tín hiệu cũng như là thiết kế, và có làm một cái demo trên một cái board của Giải. Cái topic hôm nay thì sẽ nói về một cái đề tài cũng rất là hot. Thực ra là những cái design center như trong khu vực là họ cũng đã làm cái DDR5 này rồi. Ở Việt Nam thì cũng có một vài cái đơn vị họ cũng bắt đầu làm và nghiên cứu. Thì mình hy vọng sắp tới cũng sẽ có nhiều các cái đơn vị cùng tham gia và thực hiện những cái công việc nghiên cứu cũng như là mô phỏng test các cái công nghệ nó hơi cao như vậy, ví dụ như PCI Gen 4, Gen 5 hoặc là USB 3.0 hoặc cao hơn, hoặc là DDR5. Bên phía ASIC thì ASIC là nhà phân phối của Keysight cũng được hơn 10 năm rồi. Thì các cái mảng thiết bị đo của Keysight thì Keysight có một cái mảng thiết bị đo về đo lường, về điện tử và viễn thông rất là rộng. Từ mảng về các cái oscilloscope, các cái máy phân tích phổ, các máy tạo sóng, những cái phần phân tích tín hiệu trong cái mảng 5G, 6G, hay là các cái phần liên quan tới đo compliance test, tức là đo hợp chuẩn cho các cái chuẩn về high speed digital giống như là PCI Express, Gen 4, Gen 5 hay là DDR4, DDR5. Đó thì mình giới thiệu sơ qua một tí về ASIC và Keysight như vậy để các anh chị nắm. Về cái buổi hội thảo hôm nay á, thì các cái agenda thì trên cái màn hình thời đại thì bên phía bên ban tổ chức cũng có show rồi. Thì đầu tiên thì anh Dexter anh sẽ chia sẻ một tí về các cái khái niệm cơ bản về DDR5, sau đó là những cái thách thức cũng như là những cái giải pháp về trong thiết kế, và đi kèm với đó trong các cái buổi webinar lúc nào bên mình cũng sẽ có một cái phần là làm mô phỏng trên cái tool thực tế để cho các anh chị hình dung hơn được các cái quy trình làm cũng như là các cái bước thực hiện, hoặc là những cái khó khăn và những cái thử thách nào có thể có khi mà mình thực hiện cái công việc thiết kế. Cuối cái buổi hội thảo đó thì cũng sẽ có một cái phần QA, thì bên mình cũng có những cái phần quà nhỏ nhỏ cho những cái câu hỏi theo bên mình đánh giá là hay và nó có cái tính chiều sâu một tí. Thì rất là mong các anh chị có thể là cùng tham gia cho đến cuối buổi hội thảo và đặt các cái câu hỏi, cũng như là có các cái yêu cầu gì khác nữa thì cứ cho team của bên ASIC và bên Keysight biết, thì có thể trong cái chat box hoặc là từ các cái email marketing mà bên team đã gửi cho các anh chị. Ok, thì mình nghĩ chắc là cái phần giới thiệu của mình sơ bộ như vậy á cũng ok. Mình nhắc một cái xíu luôn để cho dễ trong cái việc tương tác, cũng như là sau này mà mình có tặng quà thì lần sau nếu mà các anh chị lúc mà đăng nhập vào cái hội thảo mình sẽ nhắc mấy anh em trong team là lần sau khi mà gửi mail thì cũng nhắc lại luôn là khi mà đăng nhập thì mình ghi tên họ của mình, mà mình ghi luôn là cái cơ quan công tác, để mà biết, tại vì trong cái list hiện tại là mình thấy cũng rất là nhiều khách hàng nhưng mà không có biết là ở đâu, thì khi nói chuyện hoặc là khi tương tác thì nó cũng sẽ hơi khó. Thì nếu mà các anh chị có thể hỗ trợ được cái đó thì nó sẽ rất là hay, và cái buổi hội thảo thì nó cũng sẽ thực hiện trôi chảy hơn. Thì chắc là mình sẽ chuyển lại cái phần trình bày cho diễn giả là anh Dexter Lee bên phía Keysight. Hi Dexter, I just give a brief introduction, like explain to you. So
Okay.
I hand over to you. Thank you so much for your support.
No problem. Right. So hi everyone. Thank you, Phong, for the introduction. And also welcome to the third series of the high-speed digital session. For those who join us again, welcome back. And for those who are new, welcome, and hopefully you can join us for the remaining high-speed digital webinars in the next few months. So without further ado, let me quickly share my screen, and then we will go into the discussion here. Oh, sorry. Need to do a reshare. Okay. Right, so hi everyone, I'm Dexter. I'm the solution engineer for our PathWave design products, covering for like ADS, EM Pro, System View products, and Genesis, and so on. All right. So today's topic, we will focus a lot more about DDR5 memory designs, some of the things that you need to know when you are working with designing DDR5 products. All right, so we'll start with the technical discussion. So let's first start by looking at the typical DDR5 application. We first understand what are some of the terms that will be used throughout this seminar, so that you can understand what are some of the things that we'll discuss later on. So right here, you can see this is a typical DDR5 application whereby on the left, you have a memory controller whereby a CPU is sitting inside a package which is mounted on the motherboard via a mechanical socket here. The traces here are routed on the motherboard. It could be the single-ended, which represents the data, the DQ signals, and it could also be differential, which is for the data strokes or even for the clock signals as well. The traces are then connected to the DIMM. It could be 1 DIMM per channel or 2 DIMM per channel here. Basically, it's the plug-in module, as you can see. And on the DIMM here, basically, you can see is the memory devices. In this case, it could be a DRAM, which is mounted either side of the plug-in module here. So this is sort of a typical setup when it comes to DDR5 application. So as we turn our attention to DDR5, what does it really mean, the success for a product with DDR5? Well, it could be, bringing a product that is ready to manufacture, whereby you bring that product into this kind of environmental chambers, where you do a series of different memory stress tests. This kind of stress test, it could be ranging from different configurations such as, looking into different temperature corners, looking into, if a product consists multiple vendor DIMMs, or looking into 1 DIMM slot or 2 DIMM slot on your design here. With that, then we run a series of tests through the diagnostic software, whereby it really stresses the memory product or the device. And what we really want to see is that, we expect a graceful performance with minimal degradation, and we do not want to have any major big system shutdowns here. At this point of stage, if we start to find issues, then it could be really time consuming and troublesome to troubleshoot. And this is where we really need to have a predictive and a productive design flow to really try to minimize the probability whereby during the testing stage, we start to find issues with the product here, or even for the first prototype. So with that mentioned, what we really need is a product. We really want to get our product, our DDR5 product to really first to market. We want to market our product as soon as possible here, which means that you really need a complete design and test workflow from the modeling of the product all the way to first prototype test or even final production test. So Keysight do have a complete design and test solutions for DDR5. Starting for looking at the probing, whereby we talk about the interposers, the risers, and so on. Even for the text test fixture for the receiver, we also cover the test, the transmitter test, offering low noise scope, and then also looking at receiver test, um, which is something new for DDR5. We shall go through more on that. Of course, not to forget, we also have the modeling and simulation. And we also cover on power integrity and also looking at the protocol here. So for Keysight, we really provide a complete design and test solutions here. Some of the things are interoperable or they are linked. And the key thing is that when you work with this kind of complete design test solutions with Keysight, any point of stage whereby there's issues, basically since it's all Keysight products, we are able to support you fully throughout your whole design to test cycle right here. So how do we get to DDR5? Well, for the earlier speed grades, looking at DDR2 or DDR3, the PCB traces are mainly transmission line, I would say. So some of the key things that we look at are time alignment. In this case, we are talking about skew. And we also want to make sure that the setup and the hold times are being measured and protected as well. So that's for DDR5, DDR2 and 3, something simple. And then we move on to a higher speed grade, right? For DDR4, we are looking at 1,600 mega transfer per second and to about 4,200 mega transfer per second here. So this is where, as we go to higher speed grades, the unit interval starts to become smaller, and you start to see that the I starts to get eaten up by jitter. So this is when the industry or JEDEC starts to specify the signal quality based on this kind of box. We call it the I mask, which is really originally taken from the SERDES application here. So basically with this I mask, it indicates that as long as your signal stays outside of this kind of I mask, it can guarantee use a system bit error rate of 1e to the power of -16 here. Right, so that's for DDR4. And now we are starting to look at DDR or even higher DDR memories, right? So for DDR5, we are looking at a mega transfer rate of 4,200 to all the way to even 8,000. And this is important and crucial because for applications such as the server applications, by the time the signal propagates from the controller to the input of the DRAM, that's where you start to see the I starting to collapse here. All right. So for the DDR5 specifications, it really talks about bit error rate jitter specification, and also looking into impulse response and how we can actually recover that impulse response to give us a good signal quality here. Right. So with that, I will then share with you some of the DDR5 challenges that we'll discuss about, such as looking at the crosstalk, jitter, and bit error rate specs. Looking into in situation whereby there's close eyes, we need to start looking into equalization and even training to start to give us a more open eye. And of course, lastly, I will share more about the solutions that Keysight have to offer in terms of simulation and modeling for DDR5 and LPDDR5 systems as well. So let's talk about the first challenges, looking into crosstalk, jitter, and bit error rate specs. Well, for crosstalk, it becomes more significant at higher frequency. So one example I have here is if you can look at this eye diagram here. All right. We are looking at a DDR5 example where the speed rate is about 4,800 mega transfer per second here. So this I is closed mainly because of inter-symbol interference, ISI, from the channel. So it could be due to impedance mismatches. Right, so this I here, it does not have any crosstalk, no jitter. So you see that basically the I is very open, and you can see in the middle is the I mask that could be defined by the JEDEC specification here. Right. So this signal will then propagate to my example channel here. This is a very sort of simple design for DDR5 application, just a couple of inches. And if I do a near end and far end crosstalk simulation with my EM simulation tool, known as SI Pro, looking at the Nyquist rate, we see that the crosstalk is relatively low, below minus 25 dB. So this means that this channel is good to go here. All right. So yeah, such EM simulation is crucial to capture the crosstalk. And one thing that really contributes to high crosstalk is this kind of sharing of ground pins here. So in the case of DDR5, we have a lot of signal pins, which is represented by the kind of positive indication, but we do not have a lot of ground pins here. So one key thing is that your EM simulation must be able to accurately capture the true return path of your signal here. So in this case, looking at this diagram here, we have two signal pins sharing a single common pin here as the common reference ground here. So because of such configuration, this can actually contribute to high crosstalk here, and your EM simulation, for example, in this case, like SI Pro, must be able to effectively capture this kind of effects here. Right. So if we do a measurement in the simulation world, for example, we measure at the receiver here, and we can start to see that because of the crosstalk effect, it could be due to the high frequencies, it could be due to this kind of sharing pins. You can see that the I become closer, and this start to reduce our voltage margin. You can see that the crosstalk also starts to add jitter here. All right, at the edges here, you can see that towards the width of the eye gets narrower as well because jitter has been included due to crosstalk. Right, so crosstalk is one important effects that you need to look into when it comes to DDR5 design. And then we can look at jitter as well. Jitter is more critical at DDR5 speeds. So one example on the left I have here is a DDR4. The speed rate is slightly lower. It's about 1,600 mega transfer per second here. So again, we take a simple signal here, and then we measure the eye. You can see that the eye is very open. Probably the reason why the eye is closed is because of the ISI from the channel here. So we apply just 0.2 UI of jitter to the TX. You can see that at the cross point here, there's some jitter being applied. But the key thing is, if you look at this red contour here, right? This is the red contour that represents the bit error rate of 1e to the minus 16 here. So from this contour, you can see that there's still some spaces, margin between the eye mask here, right? So we can still have some leeway when it comes to designing the channel, and and so on. Now, if we look at DDR5, we are looking at a higher speed rate without jitter, right? With the same thing, just SI from the channel, you can see that the eye is still relatively open for the bit array of 1e to the minus 16. And then if we start to apply the same thing, 0.02 UI of random jitter, you can see that there is a 47% reduction in time margin, which is a lot. And you can see that the red contour is getting even narrower as before towards the eye mask here, right? So this reduces your design margin, and that's why jitter is one thing that you need to consider as well. All right, so we have been talking about jitter a lot, and this actually relates very closely to the specification that is defined by JEDEC. So if you look at the specification, the details of the specification focuses a lot about jitter. The spec could be talking about the maximum jitter that is allowed at certain location of your design, either the TX or the RX. It could be talking about what is the minimum UI, in this case 5.3 e to the minus to e for this kind of system, bit error rate 1 e to the minus 16. So there is a lot of details of the spec talking about making sure that under certain conditions where you add on jitter or add on certain configuration, we need to meet certain requirements such that the system is able to achieve the bit error rate of 1 e to the minus 16 here. So with this kind of jitter requirement, there's a new receiver stress eye test requirement for your DRAMs or even for your DIMM here, whereby you need to create a stress eye that's calibrated to a specific height and width. And with that stress eye, you feed that signal into the DRAM, and then you measure the output and see, when you measure the output of the DRAM, does it meet the specification that is specified by the JEDEC here? All right. So for this new receiver stress test, I will share a little bit more. It's something new that in the previous DDR4 is not a requirement. All right. So you can see DDR5, there's a lot of requirements, a lot on jitter that you really need to focus on. So in summary, the key takeaway for the first challenges is that jitter and crosstalk are very significant, as you can see for the examples here, comparing DDR4 and comparing with DDR5. And the simulation must be able to predict the eye closure effectively, looking into very, very low bit error rates such as 1e to the minus 16, and also able to capture this kind of jitter effects as well. And lastly, of course, your EM simulation must be able to capture the crosstalk accurately, meaning that you must make sure that you define your ports, your positive and negative pins accurately, so that your EM simulation is able to capture this kind of effects critically. All right, so moving on to the second challenges is on the equalization and the training. So for DDR5, something new is that we are going to add the decision feedback equalization to our DRAM here. This is something new. So basically, for example, we have a clean signal, a nice square wave that is transmitted. And after going through the channel, we start to see that the pulse started to get delay. And this will actually contribute to the intersymbol interference here. While this signal can get recovered, basically we go through the DFE block. So this is a DFE block which I've covered during our first high-speed digital webinar series. So basically the main objective of the decision feedback equalizer is to apply certain algorithm, and eventually the pulse will be equalized to a shape like this. And this can actually help to resolve the ISI issue here, right? So with that, this can help to make the eye more open and you get a better signal quality here, right? So the challenge for this when it comes to simulation is that if you look at this table here, basically these are the parameters that are linked to the decision feedback equalizer. So how do you know, which settings is suitable for your channel here? So this is, you can see that for variable gain, there's, certain gain values. The VREF has certain offset steps that needs to be taken into account, and also the multiple DFE tabs here. So the key thing is that for your simulation, you must be able to sort of do a batch simulation to sweep to all this kind of values here. And after you do that batch simulation sweep, you sort of from the results look at which set of configuration give you the most number of eye, and that's where you can start to place this kind of configuration to your design here. All right, so now we need to include the DFE portion to our DRAM, and usually the DRAM, the decision feedback equalization is represented by the die here. Okay, so if we look at traditional DDR specification measurement point, it's usually at the ball of the package here, which is physically able to measure, but it might not be possible for the die here, right? So for the DDR5 receiver specification, we need to measure at the point which is after equalization here, all right? Which is, it could be based on inferred or stimulated here. So with that, how do we do that test, right? That measurement here. One example is, let's look at the TX, which also would have its own equalization here, for example. So you can see that Keysight can actually perform such measurement. So we can look at an example here, whereby we still use a Keysight equipment to physically measure at the ball of the package here, right? The DRAM ball. So we get this kind of measurement here. Then we use the Keysight InfiniSim to actually do the de-embedding of the package model. And we also apply the receiver equalizer here. All right, in this case, sorry, I think this is supposed to be the RX test. All right, so basically what we are doing here is we de-embed the package and then we apply the equalizer here. And then from this equalizer, you can find the optimal number of taps that is required based on your channel that you have designed earlier on. So from this optimal tap that the equalizer has determined, it will then apply to the waveform. And then you can, basically we have a virtual probe within the Infinity to look at this kind of waveform and look at the eye, how open it can get after we apply the equalization here. Right, so this kind of testing approach is something different. It's not something that we do with DDR5. This is something new that Keysight have for the DDR test, right? So again, likewise, there's something new with the DDR5 receiver in the DRAM, whereby it actually has a dedicated I/O pins for the loop back mode. So what it effectively does is that this dedicated I/O pins will actually output a certain signal that is after equalization to the equipment here, right? So one example here is that I have a Keysight beat error rate tester. This tester here will consist of the victim pattern generator, which includes the random jitter source and also the sinusoidal jitter source. To add on, there is also a aggressor signal generator. So a combination of this will really give you a calibrated, very stressed eye, whereby the eye is not really open. And this signal will then go through to your DRAM, and then your DRAM or your DIMM, and then you'll go through all the equalizers and so on. And towards the end, the equalized waveform will then output to this dedicated I/O pin, which you can feed in back to your Keysight beat error rate tester, which consists of the analyzer portion, which can start to look at, whether the measured I is it within the specification here, right? So again, this is something that your simulation must be able to do as well, to include all the equalization, after the signal going through the channel, and then do that measurement and display that eye diagram for you after going through that equalization here. So this is something that is done in the measurement. So this is something also possible in the simulation, which I will show you in the demo later on. Another thing that is required that we need to take note of is skew adjustment with right leveling. So skew adjustment is not something new. Even for the traditional older DDR2 or DDR3 series here, we always talk about skew. All right, and the biggest challenge for the designer here is that when they route the PCB trace on their board, for example, like flyby technology, the clock is inevitably skewed to the data strobe, and then the data strobe are inevitably skewed to DQs as well. And because of this kind of skew, you get a very sort of a closed eyes, and then you have lesser design margins as well. All right. So basically, the DDR5 controller has the ability to adjust the skew between the DQ, DQS, and the clock signals here. All right. So basically, the right leveling capability allows the DQS to be adjusted to the clock, and likewise for the individual DQs, it will be aligned to the DQS as well. So eventually, after right leveling, you will get this kind of aligned sort of signals, which eventually, when you look at the eye diagram, it gives you a very open eye here. All right. So right leveling is something that we also need to take into account as well. Right, so the key takeaways for this second challenge is that you need to be able to measure the closed eyes, not just at the input, but also after equalization, how are you going to measure that eye? All right. So the optimal eye openings depends on, for example, the DREF settings, the gain, the DFE tabs. If you remember, I talked about the batch simulation. So your simulation must be able to support batch simulation, where it splits the various parameters here and find the optimal required settings that give you the most open eye depending on the channel that you are working on. All right, and even for right leveling, whereby it performs skew adjustments so that it gives you a more open eye at the transmitter side so that you have a bigger design margin for your designs. Okay, so with that, let's look at some of the innovations or solutions that Keysight have when it comes to simulation and modeling for DDR5 and LPDDR5 systems here. Right, so the first thing is, introducing IBIS AMI for DDR signals here. So AMI is something new for the DDR designers. In the past, for DDR2, 3, the designers really focused on IBIS model, whereby the IBIS is sort of a file representation of the IC chip circuitry. Is IP protected, and this DDR designers has been working with IBIS as well. So now with DDR5, there's an introduction of the AMI portion. So this AMI portion is actually brought over from the STRDES application here, which it really represents the equalization. And the AMI portion is really, really flexible. IBIS is a single file, and then AMI is another separate file here. So what how these two combines together is that basically we just define the algorithmic model parameters into the IBIS, just a few lines, one or two, and then it becomes a IBIS AMI file here, which can then be used to the simulation here. So it's really flexible. Basically, you can see I've listed down for you what are some of the benefits that IBIS AMI is able to offer here. Basically, IBIS AMI file, you can work with various EDA vendors tools. It's IP protected, so the circuitry of the vendors, the chips here are all protected, are all consumed in the model in DLL or shared object file. One good thing about it is this interoperability, meaning that you can get different IBCMI file from different vendors, like from Micron, from Xilinx, and so on. And then you can put them within a single simulation and do your eye diagram analysis here. Okay, AMI supports non-linearity as well. And the good thing about IBCMI is that you are able to get ultra low bit error rate, for example, like 1e to the minus 16, within seconds instead as compared to the traditional SPI simulation, which could take a couple of days here, right? So IBCMI is something new that is introduced to the DDR designers here. So how does standard IBCMI works? Basically, this middle portion here, this is something very familiar to the DDR designers here, whereby you have a standard IBIS model connected to the channel here. Right now with the AMI portion here, basically for the TX, the AMI will be added before the IBIS and the RX will be added after the IBIS here. So how does IB's MI work in this case is that firstly we have a step size pulse waveform that is used to actually characterize this channel performance here. Once it has been characterized, this step waveform will be transformed into an impulse waveform, which will then pass into the AMI portion, and then combine it with the various impulse response, and then it will construct into the full waveform here. So basically, the output of the AMI is that you get a post equalized waveform after going through all the equalization, and what you also get are clock ticks. So basically, clock ticks indicates to you where you need to sample your waveform in order to give you an open eye here. Basically, you can also do back channel interface with AMI. Basically, what it does is that the receiver will communicate with the transmitter, and then it will start to do that training, from equalizer to training to converge, or even indicates to you that whether the interface has failed as well, since the infrastructure has been in place. All right. So IBCMI is something new, and this is how IBCMI works for a simple channel simulation. Right, so this is also an important slide about what you really need to know about DDR5 signals here. So for DDR5 signals, the DQs and CA are mainly single-ended, and the key thing is that they have both the differential and the common modes here. This means that there will be DC offset for your signals, and when you construct the eye, you can see that basically the single-ended signals have a DC offset. Mainly, you can see that the signal is having a voltage swing from 0.55 volts to 1 to 1 volts. The single-ended signals has asymmetric rise and falling edges. This is due to the fact that the I/O of the transmitter, for example, has them to be pseudo open drain. This means that they present different impedance when you're driving a logic 1 or a logic 0 here, right? So because of this asymmetric rise and fall edges, you also get a asymmetric eye, all right? And then from this asymmetric eye, you can then, get the VREF calculation and start to look at the, use that VREF value for your other margins as well, okay? The key thing to take note is that for DDR, the receiver does not have the embedded clock as what the SerDes application is. All right, basically the DDR application, it uses the external clocking, which is sort of like your DQS, your data strobe, to do that clocking as well. So in this, which is shown right here in this slide. All right, so there's two situations. If your DQS and your DQ have correlated jitter, then it cancel out, and that's great, you won't have any issues here. But in situation whereby they are uncorrelated, the jitters are uncorrelated in the DQ and the DQS, then this will cause issue because the jitter will get added up, and you might get a very closed eyes, and basically have a reduced design margin here. Okay, so these are some of the things that you want to take note when it comes to understanding the DDR5 signals here. Of course, another thing is, AMI modeling is something new to most DDR designers. Right, so with that, basically, Keysight have come with an innovation solution to address those challenges that we have discussed earlier on. All right, so basically, it's the ADS memory designer here. So basically, within one simulation, you can actually take into account of multiple TX and RX, right? Which is important within one simulation. And this is important because, as you know, for DDR application, there are so many transmitter. For example, like 1 byte, there are 8 bits. So you have 8 DQs that you need to simulate. And we can also talk about multiple rank, right? Sometimes you have 2 rank, for example, whereby you need to simulate with 1 rank being terminated, and the other rank being terminated by the one die termination here. All right, so we have solutions that cover for multiple TX and RX within one single simulation. We are also able to effectively take into account of the asymmetry rise and falling edge. Basically, we have a rise. Basically, again, using the step response, our memory designer will be able to effectively capture the impulse response. And then from that impulse response, we apply, we combine it and construct a full waveform, which the waveform will be applied to the AMI model together with the DC offset here.
Dexter,
Yes.
sorry to interrupt. I
Yeah.
see some question. Do you think you can take it now or you answer it later? Because there's question about the information you presented, and I think if you explain now, maybe it's easier for the customer to follow.
Sure.
Can you take a look at that?
Sure. Okay, let me take a look. Okay. What is the reasonable value for random jitter at specific data rates such as 6400? Well, this is a very good question, and I think it's very challenging as well. So I would say typically it still goes back to the JEDEC specs. What is required to be applied in order to give you an open eye here. So again, go back to the JEDEC specs. I can get back to you, what is the reasonable value here for such a high data rate here. So no worries, we'll capture that question and then I will follow up with you again. But I would say, back to the verification, always look back to the JEDEC specs. Probably it will define the required jitter that you need to consider. And then from there, you pass it on to your design and see whether it gives you the open eye, whether your eye does it, at least the eye doesn't overlap with the eye mask here. Okay. Minus 25 dB facts to be lowest for all data rate. Or is there any facts requirement at a specific data rate? I would say this is not really all right. I would say yes, the first part is that minus 25 facts seems to be a good matrix. Of course, you can always raise the bar higher, giving yourself minus 30, all right? Because when you start to work with the JEDEC specification, that when it comes to those kind of testing, you might want to give yourself more leeway at times. So I do know some designers are more strict. They go even stricter than the JEDEC specification. They go to even minus 30 dB. So minus 25 could be a good reference point, but if need to, you can always go stricter so that when you go to the testing phase, at least there's some leeway for that testing phase. All right. So I would say that minus 25 or minus 30 is a good start. Well, at any specific data rate, that data rate will determine the Nyquist frequency. All right, so if you go to a higher data rate, then of course your Nyquist frequency, if I go back to my slide, right, so if you look at a higher data rate, then you are talking about even higher frequencies. Then, probably this might not pass because you're going to have very high crosstalk here, about minus 20. Again, it depends on designer, but in my case, I prefer minus 25. So again, if I look at higher data rate, then this is Nyquist frequency and definitely it will not pass. So I would say that when it comes to data rate, you have to look back at the Nyquist frequency, and then from there you look at whether minus 25 is the required passing point that you want to look at. Okay. What is DFE tab? Let me just go back to the DFE slides. So DFE tabs basically, if you look at here, this is not a very good slide. It's a very brief slide. Because in the first series I shared more about DFE. So if need to, I can follow up with you on that. Hopefully, we have your email address. But basically, DFE tabs are some tabs that it configure your precursor and post cursor from this precursor and postcursor here, you know, it will start to apply the equalization to that signal here, and you get this kind of sharp shapes here. So as you increase the number of taps here, you know, you can help to sharpen that dip here, all right, instead of a curve, all right. If you increase more tap, you get a sharpened dip here, all right. So in the brief explanation, I would say the taps here defines the pre and post cursor on your impulse response here, and then it will then apply to your impulse response, and you get this kind of shape here, right? So this is a very brief slide. If you need more technical details, I have the slide for the first series webinar. I think as a follow-up, we can follow up with you to explain a little bit more about DFE tabs. Okay. But yeah, DFE tabs is used for equalization. Eventually, you know, you want to switch to different tabs to see how much you can get an open eye here. Okay. Let me see if there's any questions. Yeah, so we'll capture your names and your email address, and then I will follow up with you on the necessary documentations. Okay. Okay. No questions. I will move on. For time's sake. Yeah. So I've addressed this. So again, the memory designer will cover all these features here. And one important thing and is unique within Keysight is that the memory designer here is that our simulator is able to pass both the DQ and DQS within the same AMI model file. And this is important because you know, we talk about DSkew, right? DSkew between the DQ, the DQS, and the clock. So again, you know, the RX we represent by a single component. So, you know, just that within single component is able to do that DSkew internally by itself here. All right. So this is something important as well, both the TX and the RX side. Okay. So one unique approach that Keysight have is also on external clocking. This is where we talk about the gateway 2 function, which is something added on to the DDR5 application. Basically, the gateway 2 function, the main purpose, you know, in general is able to help to deskew to make sure that the DQS is aligned to the clock, and then also making sure that the DQ is aligned to the DQS as well. So if you take a look at over here, this is data stroke that is fit into the controller. If you remember the controller, we talked about right leveling, right? So this data stroke will then be fit into this input here, which is this PI block here. What is this PI block? Basically, it is a phase interpolator. The main purpose is that, you know, is able to do a fine control to the DSkew, to the data, to the DQS, so that it's aligned with the clock as well. All right. So this is something that you see in the controller, as mentioned at the right leveling. For the DRAM, the DQs, for the DRX side, you don't see this phase interpolator. All right, because some of the EMI will then already account for the DSkew, right? So gateway 2 is something that is introduced in the controller, and for us, memory designer, we do have this gateway 2 capability introduced, right, to make sure that everything is DSkew and everything are aligned together. Okay, so if we look at the how the phase interpolator actually contributes to the eye, we can take a look at this few eye diagram here. All right. As usual, we measure at the RX package, which is we measure at the DRAM ball here. All right. So if you look at this plot here, if we don't have the phase interpolator, the gateway 2 output, then you can get a very close eye. All right. But then, if we start to include the phase interpolator training that is inside the memory designer here, that's where we get an open eye here. All right. So this is something that our memory designer is able to cover. And then you make sure it's cover all aspects that you are going to do at your measurement as well, so that your simulation correlates well with the measurement side. Right? So basically, in summary, before I move on to the demonstration, basically ADS Memory Designer, it reduced your simulation complexity in the sense that now your setup time for the simulation reduces from hours to minutes. In the past, before Memory Designer was created, in the past, even in ADS, we have to manually, set up the individual transmitter, individual receiver, and then we have a channel in the middle whereby we have to manually connect, wires to every single channel with the TX and the RX. So this sometimes can be very time consuming, and it can be very error prone here. So later in the demo, if you see in Memory Designer, basically it's just a single bus wire. You are able to set up the connection for all the TX, RX, and the channel. Again, so one schematic for the DDR bus and transient simulation, you can apply IBIS AMI as well to a group of signals, not just one. You can just assign it together. Simple wiring, the bus wire which I talk about. Test bench for pre-layout and post-layout. All right, so if you remember my first part of my high-speed digital webinar series, we talk about pre-layout using controlled line impedance and also VR Designer. So that is also applicable for your Memory Designer flow as well. For the post-layout, if you talk about SI Pro, if you remember my second series, we talk about SI Pro doing signal integrity EM simulation. So even for SI Pro, whatever you have simulated, you can quickly export it into your schematic and run with Memory Designer here. Okay, so easy EM setup. And then likewise, SI Pro will be able to capture the critical effects like crosstalk, and then you can do the measurement for a group of signals within one single simulation. Okay. So without further ado, let me go into the demonstration. Okay, I still have a couple of time. Okay, so let me just launch my ADS here. All right, so you can see that on my screen, this is a typical Memory Designer setup here. On the left, you can see that we have the controller and then the printed circuit board and the DRAM here. All right, so how is the printed circuit board being set up? All right, so what I can do is let me launch my SI Pro. All right, so this is the board that, for example, today I'm interested to simulate. Oh, I have to apologize as well, because for the demonstration workspace that we have, currently we only have the DDR4 application. So this demo will be based on DDR4, but do not worry, the workflow and the design flows are still very similar when it comes to DDR5. Some minor settings like VREF, might be a little bit different, but the workflow on setting up the simulation and analyzing the results are pretty much the same. Okay. So what I have here is a DDR DIMM board for DDR4. And today, I'm interested to simulate the U1 DRAM and the U19 DRAM here. All right. And then, this DIMM card will be connected to the controller, which is based on J1. So this J1 will be defined as my controller here. All right. And the good thing about SI Pro is that we have the DDR wizard, the setup wizard, whereby through a few clicks on the SI Pro, you are able to set up the EM simulation quickly. All right. So one example, okay, if I launch my DDR setup here, all right, for today, I'll be simulating at 3,200 mega transfer per second, but you can choose the speed grid that you're interested to look at, and then that will automatically define the rise time and the maximum frequency that you need. All right, this is the I would say I think usually we do 5 times of the Nyquist frequency so that we really capture the harmonics as well for the simulation. Okay, and then the signal voltage, depending on what you want to operate, you can always change it as well. All right, so we're going to add in the memory controller here. So what I'm going to do is I'm just going to click on J1, And then I'm going to click on select. This will bring in J1 for me. And as mentioned, my memory devices today, I want to simulate, I want to include U1 and U19. So what I'll do is I'll select U1 and U19, and I will add them to my memory devices. And within a few seconds, you can see that the DDR setup actually add in all the necessary signal nets for the DQ, the DQS, and also the power nets, the VDD, and also all the necessary capacitors that are typed, from the memory controller to the DRAMs here. Okay, so I can then generate a DDR analysis. Okay, generate analysis anyway. And then you can see that basically the controller and the memories are being set up for you. You can see that all the ports has been automatically created for you. Right, likewise for the DRAMs, those ports that are associated with the DRAMs to the controller, all these are automatically added for you. Okay, so we can really take a look and confirm, whether are we getting the correct signal nets from the DDR setup here. So we can, highlight all the nets that has been included and on the ports. And you can see basically, yes, these are the main key nets that we want to simulate from the controller to the necessary DRAMs here. Okay, so the VDD are included as well, the power plane as well as the ground plane, right? So all this will be added as part of your simulation here. Okay, so the good thing about SI Pro, for those who are new to SI Pro, you can see that the simulation setup is net specific analysis. So you only need to specify the nets that you want to simulate today. This means that you do not need to do any cookie cut. You do not need to do any modification to your board to reduce the simulation time. All right, just specify the nets you want to simulate, and SI Pro will do the necessary algorithm computation that you need to simulate and get the results as soon as possible, but without losing the accuracy here. Okay, so for those who are new, basically SI Pro, the EM engine behind it is a composite of the momentum and the FEM simulation. All right, just a brief introduction here. Okay, so basically we are done with setting up the ports and defining the nets that we want to simulate. The next thing is the component models here. So you can see that basically there's a warning message saying that the models are not being defined here. So again, for those who are new to SI Pro, basically for this kind of component models, SI Pro supported the following, such as adding a simple lump component. If you have any SMP file that you want to use, it could be taken from some vendors who are, who have the SMP file, you can always use it as part of your simulation as well. Model DB, model database, this is based on the database that ADS have, which consists of, like, for example, Murata capacitors, inductors, TDKs models as well. So we have a database that you can use to include in your simulation. And of course, library cells, sometimes some designers want to include SPICE model files, so they can include such SPICE model files to represent your components here. Okay, so I've already finished the setup here, which is shown right here. And then what I do is basically I run this simulation. All right, again, you can see the DDR speed, all this has been configured. And then I can take a look at the results, for example, looking at skew. Right, how much skew is it across between the DQ and the DQS, for example? You can get this kind of results right here. Of course, you can look at the S parameter results, right? Just for example's sake, let's just look at the true of all this, all right? Plot insertion loss, and again, you can look at these results here. And of course, you can also look at the TDR, right, to look at the response here. So TDR is a really good tool to troubleshoot and really look at, check your impedance and to check whether is there anything gone wrong with your design here. Okay. So the cool thing is that SI Pro, whatever you have simulated in this SI Pro EM simulation environment, you can quickly generate a sub-circuit, which then you can bring it into your schematic and run with your memory designer here. Okay, so basically what I have already done is I bring in my SI Pro EM simulation results, and you can see that it's quite automatically. All these ports here are defined in the SI Pro, or rather on your layout. So memory designer is quite smart in the sense that it's able to, from the port name, automatically assign the signal type, and also looking at the index, and then you will assign the signal index in one. So this DQ0, DQ1, and so on. Of course, if there's anything wrong, you can always change the signal types. All right. So depending on the I would say the memory that you're working on, be it DDR5, DDR4, DDR6, or GDDR6, and so on, this signal types will change accordingly. Okay. And then we are going to just simulate a single channel here. So we just indicate everything in 0. All right. So this is the setup for the channel here. All right. And then from the controller here, all right, if I double click, basically what I'm doing today is basically I'm simulating with a generic DDR4 IBIS file that Keysight have. All right. And then we'll add in the RRC package information as well. So as this is a controller, which is J1, if you remember, I'm going to enable it as yes. And today, I'm just interested to look at the DQs, right? Just for simplicity, for simple sake. All right. So basically what I did is I enable, basically, I only enable the DQs for J1, all right? So you can see 1, 0 to 7. This is what was shown earlier with our SI Pro channel, if you remember. So basically, I enable just the 7 channels here. Of course, if you want to include your data stroke, you can always include it as well. For today's demo, for simplicity, I will just simulate this 8 DQs. Right? So we can go to the model setup, right? The DQs, all right? Basically, these are the 8 DQs that I want to analyze. What I've done is I've grouped them together, right? Since they're going to, share the same IBIS MI details here. All right, so you can see basically I can set a lot of things. I can choose the IBIS model selector, be it 40, 48, or 60. You can even look at the different corner types. If there's any equalization, for example, the FRR tabs, the de-emphasis, the jitter, the PRBS, you can always set this up. And by this kind of grouping, basically, whatever configuration you've done within this single window, it will then be applied to all the TX for the DQs as well. Okay. So this is the setting for the IBIS MI for the TX. And likewise, for the RX as well, I've enabled U19 and U1. And again, selecting the 8 DQs that I want to analyze. Okay. And even for the model setup, I've grouped them together. And again, specify the IBIS model that is associated with this RX component here. Okay, and then again, there's DFE, FFE, DFE. All this you can include in part of your simulation as well. All right. So this is something new. You might also notice that on the right-hand side, we have this variable for batch simulation. So remember one of my slides, I mentioned that designers need to sweep to various DFE tab settings, or some designers even sweep the different IBIS corner types here. Right, so do take note, memory designers support batch simulation as indicated here, batch sim. So today, due to time constraint, I'm not going to go through that, but do take note that it's supported as well. All right, so for the connection, it's very simple, just a simple demo here. Basically, it functions by bus wire. If I do that simple connection, you can see that this window pops up. You can see all the, the signal IDs are being shown right here in this window here. So what we only need to do is do a connect all. All right. Basically, how this works is that the signal IDs must be the same from the controller to the PCB. All right. As long as the signal ID are the same, the channel ID are the same, memory designer will be able to quickly know which are the connections it's able to make. And then there you go, done. Just a single connection. So the same applies, from the PCB to the RX as well. Just a single bus wire, we already, do that connection here. Okay, so that's our simulation, setup from the TX all the way through the channel and then through the RX as well. How about the measurement? We use a memory probe. So this is the memory probe whereby, we set up the probe. Again, you can set up the single-ended voltage for the DQ, the clock. You can look at advanced settings here. Yeah, center the eye in transient and statistical modes and so on. Okay. There is one portion on eye mask. Let me see, where is it? There's a portion on eye mask, so you can actually use your custom eye mask to place it right here. Okay. So again, as mentioned earlier, your JDEC specification, you have eye mask. So you can indicate your eye mask right here. Okay, to feed in your JDEC specification. And then, as mentioned earlier, we are going to simulate the DQs from DQ0 to DQ7 here. So what we're going to do is, I've basically added the DQs that I want to simulate into my RX portion here. So if you remember, we talked about measuring from the DRAM ball. And then because of the technology whereby equalization comes in, we need to measure, or rather, placing a virtual probe at the die of the DRAM here. So this is what you're looking at, the RX output. This is the point where it is measured after the equalization here. You might have noticed, hey, the U1 and U19, there's also DQ0 to 7. What does this represent? This is before equalization, meaning that it's at the ball of the DRAM. All right, so RX output means at the die, meaning that it's already passed on, we have already applied equalization to our signals here. All right, so likewise, in the simulation world, we can do such similar things with the measurement as well, measuring at the ball of the DRAM and also applying after the equalization. Okay, so we're going to do this simulation, and then again, you can look at what simulation results that you want to look at. You can look at the eye density, you can look at skew, mask margin, and so on. Reference signal, this comes in if you are looking at data strobe. All right, so I won't go through in detail because I think there's not much time left. Design exploration, if you have certain sort of JDEC standards, certain file format that you want to use, the JDEC, you can always use it. But we also have another option for you to see whether your design fit into the JDEC specification, which is the compliance test bench. All right. So I will talk about that later, but this is mainly the setup that we'll be looking at for our simulation, right? Mainly looking at the eye diagram, that's all. Okay, so before I run the simulation, let's take a look at this memory designer setup here. So as mentioned earlier, I'm going to simulate, I'm going to look at my simulation at DDR4. Just an update with our latest ADS 2023 release, which is released just, I think, 2 months ago. We are starting to support more and more latest memory technologies. We do support like GDDR6, looking at high HBM3, and even the latest one we added in is LPDDR5X. Okay, so if you are looking into simulating this kind of advanced memory technologies, then you can start to look at memory designer. If there's any technologies that are not supported here, write into us. We can actually raise the request and see our R&D is able to implement that interface in the next release. All right. Again, batch simulation, I'm not going to cover today, and then we're going to use DDR Steam for the simulation. Okay. So I've already run the simulation, and then, just within one simulation, you can quickly look at the eye diagram just within one simulation. All right. You do not need to run multiple simulation and look at individual eye diagram, just one. And you can quickly take a look at this kind of results right here. Okay, so this is for the, just the memory designer DDR bus simulation. Another application that we can look at is the compliance test bench. All right. So for compliance test bench, due to some configuration, talking to some of our test software like the DDR4 compliance test app and also the Infineon offline test app. Therefore, the transient simulation is required here. The only difference is that I have enabled the compliance measurement. So basically, you can see it's basically working with the Infineon compliance app, which is also done when you're doing your measurement. All right, I think this test app is also applicable when you're doing your physical measurement. So again, some of the things you are able to set, it's like supply voltage, the single handle voltage, and all this. All right, and then we set up the compliance measurement. We look at the overshoot, overshoot area, undershoot amplitude, something simple for illustration purpose. All right. So when you finish the simulation, or when you are running the simulation, basically, it runs together with the DDR4 test app, right? And then it runs with the Infineon Steam as well, which I'm sorry, it's on another screen, but I can't seem to move it. But basically, you can see it runs together with the DDR4 test app. And then let me quickly see if I'm able to get the test report out. All right. So in addition, basically when you finish the I got it. The report. All right. So basically, when you finish the compliance test set, a report will be generated for you to indicate, what are some things that fail or some things that pass. All right. In this case, just a simple example, we have a pass status here. Okay, so that's for the demo. I will quickly finish off my slides, just a couple to go before I answer the Q&A section. All right, so in summary, all right, as mentioned, for our memory designer, we can do a compliance test with our compliance test app. You can see basically the test report here indicates a fail as well. And then you can see which are some of the tests that does not pass the requirements here. Okay, so again, memory designer cover a few things: the equalization modeling, asymmetric eye shape, right leveling, compliance report. All this are supported as well. The gateway 2 approach, all right, is supported in our memory designer as well. And then as a summary again, I think this is the same slide as the previous one, so I will not go through in details due to time constraint. Just to highlight, this is a success story with one of our customer from Seiko, Italy. They are one of the leading embedded PC manufacturer here. So the challenge is that they need to establish and implement a DDR design procedure to predict any unpredicted schedule slippage. Right, so time is really a main concern for them. So the proposed solution was, ADS Memory Designer and SI Pro. And the results from this is actually, qualified by our customer, is that they actually reduced the number of PCB failures from 2 out of 10 every board, now down to, as they testify, is 0. And, the DDR products ship running at this speed grade. And definitely the key thing, that which memory designer comes into play is that it's able to shorten the design and verification time from 1 month to just 10 days. This is testified by our customers here. Okay, so in conclusion, DDR5 offer tremendous speed, but with that, there's also many challenges that we need to take account to. All right, so we really need to have a complete design and test workflow. So this is where Keysight comes in. We provide a full simulation, a complete design and test workflow, starting from the simulation all the way to the measurement for your first prototype to your final product testing. All right. So with that, thank you. Let me do the Q&A now. Just give me a minute while I launch the software.
Thank you, Dexter. Dạ, các anh chị bây giờ mình có thể đưa cái raise hand thì anh chị nào muốn tương tác trực tiếp với lại diễn giả thì mình có thể mở mic được ạ. Hoặc là các anh chị có thể đặt câu hỏi trong chatbot nếu như mà chúng ta có hơi bận và chúng ta không thể mở mic thì chúng ta có thể đặt vô chatbot để bắt đầu cái phần tương tác Q&A với lại diễn giả nha.
Okay, so I see one question. Is it okay if I address the question now? Sorry for the interruption.
Yeah, okay. Now you can answer the question in chatbot first.
Okay, sure. So the first question is, can ADS do speed test simulation and logic test simulation? So far I have not heard of that. So I don't think it's support, but let me check. So far what we really do in ADS is a lot on signal integrity and power integrity. So speed test and logic test might not be covered in ADS. But yeah, I will capture your name and your details, and then we will follow up with you accordingly. But as a quick answer, I don't think ADS support that. It's a lot more on the signal integrity. I saw. Okay. Can you explain more about memory designer in ADS? Sure. Together with Tran question, can we recombine the S parameter models of package, sockets, and PCB in ADS? I will do it together. Okay. So apologize if I went on very fast. Basically, memory designer. The main thing is that is support for memory designs. All right. So in the past, you know, for the TX, right? Let's say today you want to simulate 1 byte for your memory. 1 byte consists of 8 bits, meaning that you need to simulate 8 DQs. So in the past, you may want to individually add every single transmitter. So that will take a lot of time. The same for the RX. It's going to take a lot of time. So that's where memory designer comes in. All right. You have a single component that represents the multiple DQs, the multiple the DQS. Likewise from the receiver side. All right. And then you can see a single bus wire that set up the connection to connect the multiple TX. And then also a single wire to connect to the multiple RX as well. Right? Even for the PCB board, just a single component is able to represent the different the multiple DQ channel here. Okay. And then we have a memory probe to do that eye measurement for the different DQs here. All right. So memory designer really addresses the DDR applications. Likewise, if you remember, I talked about IBCMI. So likewise for this component here, basically is able to support the IBCMI portion here. Okay. And then as you shown in my demo, you can see that in one shot, you are able to, just a single simulation, you are able to look at multiple eye diagrams. Okay. Let me see. Okay. So I hope that explained your question. And then the second question was, yes, including S parameter, for the socket, the connectors. That is actually a very good question. I wanted to address that, but I forgotten. So we can look at this setup here, all right? If you look at a typical DDR setup, right, you will have a driver which is going through a package, the socket, the breakout, even for the connector here. So how is this set up in the memory designer? Basically something like this, whereby again you have the controller, the memory included here. The connector here you see, all right, is basically based on, I think it's a Molex DIMM connector. All right, so again, yes, my answer to you is yes. If you have any S parameter files, you can bring it into ADS and work it with memory designer, which again is based on the single bus connection wire here. Okay, what you're seeing here is, the PCB breakout and the open field. Basically what we do is we use the pre-layout to do the representation. Okay, so Yeah, this is the I think the VR connection that we have created from the pre-layout tool. Right, so you can also create such designs for your pre-layout and connect them together within a single bus wire. Okay, likewise for the transmission line, all right, you can see this is my 8 bits transmission line. I've created them and again function with a single bus wire. Okay, so to answer that, yes, if you have any S parameter files that you want to bring in, you can always use it here. Any question? I hear someone unmute.
Sorry, anh Hưng, anh có thể mở mic để mình trao đổi trực tiếp luôn ạ. Nếu mà các anh chị đang đặt câu hỏi chatbot á, thì mình có thể share lại cái application mà các anh chị đang làm. Thì như vậy Dexter có thể trả lời chính xác hơn đúng với cái ứng dụng đó. Chị Ngọc với em Trí có muốn trao đổi với anh Dexter trực tiếp không ạ?
Okay, so I see another question. How can ADS SI Pro support me in analyzing impacts of power integrity to signal? Wow, that's a good question actually. Let me see if I have an example that address that. Yes, I do. All right. So the key thing is that yes, in your EM simulation, if you remember in my EM simulation, I actually added the VDD to my SI Pro. All right. So basically what I'm showing here is the PathWave SSN analysis of data signal for DDR4 design using memory and designer here. Okay, so if I take a look at the setup here, okay, something signal. Basically, again, within the cell. So this is something to do with pre-layout. But of course, you can always add it in. You know, in your EM simulation, you have a port set up for the VDD and also for the DSS. All right. So if I open cell here, you can see basically, you know, this part will probably be your VDD part. So again, for the generated S parameter from SI Pro, you can add the VRM characteristics to your VDD, for example. All right. And then we can add it to this kind of memory pre-layout, right, for the S parameter they are working on, for example. And then indicate the signal type. And then this would be your VDD VSS connection here. And then on top is still your usual DQ signal nets. All right. So in terms of pre-layout, you know, it works on S parameters file. But if you talk about SI Pro, definitely you need to include it in your simulation. And then when you generate a sub-circuit, you will have that connection for DDD. And then again, you can use a single bus wire to connect the VDD connections right here. So to answer your question, yes, you know, the memory designer will take into account of the VDD and VSS. The key thing is that you need to have the necessary information for DDD and VSS. So in this case, you know, of memory pre-layout, it's actually having a S parameter file to represent that. At least for SI Pro, you need to include it in your simulation, which I've already done it, the VDD, and then you can include it in your simulation here. Okay. Okay, so yeah, there's one note here. Yeah. Yes.
I have another related question to the previous question. Can we achieve bit error rate of minus 16 if I want to include the impact of power integrity?
Okay.
Yes.
Definitely you know, when you include the power plane part, you know, it's going to affect the eye. Definitely, there's going to be some effect. So again, it depends on your design here. If you have a well-designed here, then I would say that there shouldn't be a problem to hit a system bit error rate of 1e to the minus 16. It also depends on your equalization as well. As you know from my sharing, you know, you definitely need equalization to give you an open eye. So I think my question is, yes, you know, if you include the power aware portion, it's definitely going to contribute something to your eye. The thing is, you know, what kind of equalization if you want to use. And looking at JDEC specs, I think JDEC specs specify 1e to the minus 16. So that is a requirement that you need to design as well. So definitely you need to design a 1e to a minus 16 system. The key thing is, what kind of equalization are you going to use to make sure that you beat that system here? And also, the gateway to clocking and all sorts of things. Yeah. Does that answer your question? Yeah.
Yeah, thank you.
Okay, great.
Yeah.
Okay, I see another question. Can Keysight fix my issue with clock in Memory Designer and update hexagon I mask? So I'm not very sure what do you mean by the clock issue. I would assume probably maybe some deskewing that's happening on. So as mentioned earlier, within the Memory Designer, we actually have the gateway 2 implementation, which is the phased interpolator. Let me open up that slides again. All right, this portion here. So this is also one solution or one unique approach that Keysight have to address all this kind of timing or external clocking issues and trying to deskew, both the DQS and DQ so that it's aligned to the clock and eventually giving you an open eye. So this is the solution and approach that Keysight has when it comes to, clocking issues. Okay. I hope that addressed your question. Yeah, so I think there's some questions that I'm not able to fully capture it. So again, I believe we have the chat box being archived. So I'll get back to you on those questions raised. If there's any document as well that I want to add on, I will share with those questions asked. Okay. Yeah, is there any questions? Yeah, for the recorded videos and the file webs, I think it should be shared. I'm not too sure. That, ASIC, maybe you can address that. Yeah.
Dạ vâng ạ. Thì ASIC sẽ đại diện cho phần của Keysight, thì về phần recording cũng giống như là các cái tài liệu thông qua của buổi hội thảo thì ASIC sẽ tổng hợp lại, đặc biệt là phần Q&A vừa rồi của diễn giả Dexter. Thì các câu hỏi này thì bên đội kỹ sư của ASIC cũng sẽ tổng hợp lại và làm rõ hơn chi tiết cho những phần câu hỏi này và gửi cho các anh chị để tham khảo. Nếu như các anh chị có thêm cái phần nào về câu hỏi hoặc là chi tiết hơn về ứng dụng của bên mình thì sau cái buổi hội thảo này các bạn nhân viên của ASIC sẽ liên hệ, thì chúng ta sẽ có thêm nhiều cái buổi trao đổi hơn. Hoặc là nếu các anh chị có muốn kế hoạch demo hoặc là các cái video mà liên quan tới ứng dụng của ADS hoặc là các phần mềm PathWave của Keysight thì các anh chị có thể liên hệ trực tiếp tại với bên em ạ. Thì không biết là có anh chị nào cần đặt thêm câu hỏi cho diễn giả nữa không ạ? Dạ. Nếu như mà các anh chị không có thêm câu hỏi nào nữa thì em xin phép close cái buổi này. Thì trước khi mà chúng ta kết thúc thì em xin giới thiệu là vào tháng 10 và tháng 11 thì sẽ có tiếp tục 2 cái buổi chủ đề nữa trong cái chuỗi series về High Speed Digital này. Thì chủ đề thứ tư ở đây là vào tháng 10 sẽ là về quy trình đảm bảo cho sự toàn vẹn của bộ nguồn và thiết kế làm sao cho trở kháng BDN phẳng. Và chủ đề thứ 5 chính là quy trình mô phỏng EMI sử dụng phần mềm ADS của Keysight. Thì để cho hai cái chủ đề này nó làm việc được trọn vẹn hơn thì nhân viên của ASIC sẽ liên hệ với các anh chị để thông báo chính xác về thời gian cũng như là cách tham gia. Thì mong và sau những cái buổi hội thảo tiếp theo thì các anh chị sẽ tiếp tục ủng hộ cho ASIC và cũng như Keysight giống như là các buổi này. Vâng, em xin cảm ơn các anh chị đã tham gia trong buổi ngày hôm nay. Thank you, Dexter. We can close the seminar now because we don't have any question more.
Okay, sure. So thank you everyone, the audience here and also ASIC team for support. Thank you.
Yeah, thank you.